Good afternoon, everyone. Today we're going to look at an example where we consider the function f of x being x squared minus 3x plus 2, a parabola, and we're asked to graph itself, its square root, and then state their respective domain and range. Okay? So before we start putting points on our graph, we could just start plotting points by plugging in different values of x into f of x and evaluating as such to get the y-coordinates, but we could get a nice few key points by looking at some obvious ones. First off, we can get our y-intercept by plugging in x equals 0, which means the first two terms go to 0. And so we have the y-intercept at positive 2. You can pop that point on our graph to begin. And next, we know we could get our x-intercepts, our roots, by writing f of x in factored form. And so we think back to factoring quadratics. And so we ask ourselves what two numbers multiply to make positive 2 and simultaneously have a sum of negative 3. Those two numbers will be x minus 2, x minus 1. And remembering that to get our x-intercepts, we change the sign of the numbers inside of the brackets. And so that means our two roots are going to be a positive 1 and positive 2. And next, we don't need the vertex, but we can get the vertex, which is good practice, I suppose. So we could write this in vertex form by completing the square. To complete the square, we're going to take half of the b coefficient, and we'll have x minus half of 3 is 1.5, or 3 halves, we're on a graph. Let's do the decimal form. So x minus 1.5 squared minus, now we just created the 1.5 by itself squared term out of nowhere, so we have to balance it out. 1.5 times itself is 2.25, and then we sum the plus 2 to the end. And so let's clean this up. So we get x minus 1.5 all squared minus 0.25, meaning that we have a vertex. We change the sign for the x coordinate inside the bracket, so that's positive 1.5, and we keep the last bit for the y coordinate. And that makes sense, right? Our vertex should be smack dab in the middle of our two x-intercepts between 1 and 2, which is of course 1.5, negative 0.25. I'll squeeze that in there just to make some arguments about symmetry later on. That's convenient. So we can also make one right now. So since our vertex is at 1.5 and the y-intercept is 1.5 units to the left of the vertex, we know that the same point exists 1.5 units to the right of our vertex, because that's what it means for the vertex to be on our axis of symmetry, right? And so that means 1.5 to the right brings us to 3, and so we get a point at 3, 2 for free, and then we can start graphing our parabola. Okay, like so. Now, if we want to graph the square root of f of x, well, first we need to think, where is f of x going to be negative? Because we know that we're never going to be taking the square root of a negative number and having it be defined. And so we can quickly tell that the only region that our function f of x dips into the negative y values is right between two x-intercepts, namely positive 1 and positive 2. That's a fairly small region where we won't have our square root of f of x function that is defined. And so let's start off by maybe we could look at the domain and range for f of x. So the domain for f of x is what? Are there any restrictions on the domain of a parabola? There are not, and so we can simply write x can be any element of the real numbers. And the range, well, are there any restrictions on the range of this parabola? Well, we know the vertex is at 1.5 and the y value of the vertex is negative 0.25, and so that's as low as that f of x function is going to go, and there's no upper limit. And so for the range, we can write y is greater than or equal to negative 0.25, and of course, once that is considered, then y can be any element of the real numbers from there. Now, for the square root of f of x, that's going to be different, right? We're going to have a domain that is restricted because we can take the square root of any number as long as it's non-negative, right? But our y values are negative, again, between positive 1 and positive 2 in the x's. And so that means that our domain for the square root of x is going to be x can be any number in the interval negative infinity all the way up, right, anywhere on the left, all the way over to positive 1, and including positive 1, because that would make the function, that would mean the function has a value of 0 there, which is non-negative, so we're fine. So including positive 1. Now, it's not going to be defined for 1, 2, and then again at 2 directly, and including 2, it starts being defined again, and onwards up into infinity. And so union, the interval of square bracket positive 2, all the way over to infinity. Again, round brackets are the infinities, because we never actually reach that point. And so now, we can also get the range fairly quickly, because if we take the square root of a function, and we already acknowledged that we cannot take the square root of any negative value, then we do have values of 0, and so we know we're going to take the square root of 0, which will be 0. So we know y can be as low as 0, but it can't be any lower, right? We can't have any negative values if we're only taking the square root of non-negative values. There's no upper limit to the values that the square root of x can take on. If fx can grow infinitely, then its square root can also grow infinitely. So the range of the square root of fx would be that y is greater than or equal to 0, right? It can't dip below 0. And then after that, y can be any element of the real numbers. And likewise, we can add that up here. X can be any element of the real numbers within those intervals. Now, let's go ahead and plot some points for the square root of f of x. So I'll make it in red. Y is equal to f of x. And then let's use a different color for the square root of f of x. So let's use the blue. So again, we can always just plot points. However, there are some nice key points that we can get fairly quickly and with little work involved. For example, at the two x-intercepts, we know that f of x is equal to 0, right? We know that f of 1 is equal to 0, and we know that f of 2 is equal to 0, right? What are the square roots of 0? Look, there's 0. So that means that the square root of f of 1 is the square root of 0, which is 0. And likewise for f of 2, right? Square root of f of 2 is the square root of 0, which is 0. And so we already get 2 points on the x-intercepts. We know those are included, right? After that, it's just going to be a matter of getting the points that we kind of want, okay? At x is equal to 3, f of 3 is equal to 2, which we found. And so that means that the square root of f of 3 is simply root 2, which is roughly 1.4. And so that's not a nice decimal, it's an irrational number, but it's not awful either. And so at x is equal to 3, our value for the square root of f of x is 1.4. We can pop that on. Let's pop it around here, right? And then we can use that for a few different points. We also get it at f of 0. F of 0 is equal to 2. And so the square root of f of 0 is equal to the square root of 2, which again, 1.4, right? We know that's the case because, again, it's symmetric about the axis of symmetry at the vertex. And so we get another point here at 0 and root 2. And now let's say we want 1. Let's do f4. We can just plug in 4 in for x. F of 4 is going to be 4 squared, 16, minus 3 times 4. 16 minus 12 is 4, plus 2 is 6. So if f of 4 is 6, then the square root of f of 4 is equal to the square root of 6, which is roughly 2.4, I believe. And so when x is equal to 4, we have a point at roughly 2.4, which takes us around here. And we know it's going to be symmetric, right? So that's 2 units away from the x-intercept, and so 2 units away bring us to -1, and likewise over here a -1 and roughly 2.4, okay? You get 1 more point if you guys would like. Let's do when x is equal to 5. So f of 5 is, we're going to evaluate this quickly, 5 squared is 25, minus 3 times 5, and it's 25 minus 15, which is 10, plus 2. So f of 5 is 12, and so the square root of f of 5 is equal to the square root of 12, or if you'd rather, 2 root 3. And that is around, root 3 is 1.73, multiply that by 2, we're at roughly 3.5-ish. 3.5, feel free to use a calculator for these irrational numbers, right? That's totally expected. And so when x is 5, our y value is 3.5 roughly. So that is around here, 5 and 3.5. And again, we get an argument of symmetry to the other side of our axis of symmetry. Right now that's -2, -2, and 3.5. And now with 4 points, we can kind of start seeing the shape, right? This is gonna curve ever so slightly, barely, because we're taking the square root of a quadratic, right? And so it's gonna look essentially more like a straight line than it really is a curve. It looks something like that. And that will extend onto infinity in both directions. And so that would be y is equal to the square root of f of x. And those are the two functions we need. So again, this looks like tedious work, but all we're really doing is plotting a bunch of points on a graph until we start to see the shape of the curve emerge, right? We know parabola is generally going to look like that, so that's a nice starting point. Now from there, the square roots, just plot 3, 4, 5 points is usually enough to start to see the shape kind of take form. And then from there, we can draw the curves on the graphs. The domain, again, we can see that for square root of f of x, not defined between 1 and 2, but -infinity up to 1, 2 up to infinity. It is defined for any element of the real numbers, and so that's our domain. And the range, right, again, we can't dip into the negatives, and so y for the square root has to be greater than or equal to 0, but from there it can be any element of the real numbers. And so our domain and ranges are justified from our graphs. So I hope this starts to make some connections for you guys. I hope you start to see how to graph radical functions, but more generally, how to graph any function that you might not be incredibly familiar with at the start. We can always just plot points, right? Even if they're not maybe the best points to start off with or the most convenient points, or the points that are most readily available, we can still always plot a bunch of points until we start to see a pattern take shape, and then we can draw that curve from there. So if you guys have any comments, questions, suggestions, please do leave a message below, and I hope this helps.